Good day, everyone. This is Vincent Tan speaking. This time, I'm going to talk about TOSO Multi VRF, short for TNV, the introduction for North American market. This is the general introduction. If you are interested in TNV specified product, please go to watch the other videos for more detail. This sharing divides into these 6 parts. I have put the corresponding video linkages at the below description area just for your reference. Moreover, I also provide the quality subtitle. Don't forget to turn it on if you need. TNV technology.
Oil circulating control technology. First, let's focus on GMV5 as we apply two oil separator, which means two-stage oil separating, and the efficiency it can be as high as 99.9%. And just for this reason, as we can separate more oil, so we can also prolong the oil return period, which to save the energy. As for GMV6, the oil separator is only one, but with two oil return passes. And here is how it works. This is the compressor, and here is the oil separator. The oil and refrigerant mixture will go through the oil separator. The refrigerant will go into the system for heat exchange, and the separated oil will go through this filter and then gets through. First is the major oil return uh, back to the compressor for lubrication. At that time, this major oil return, this valve is always open. It is quite enough for the regular condition. Here, what I mean the regular condition is when the outer ambient is not low. If the outer ambient is become very low, for example, as low as minus 22 degree Fahrenheit, which is minus 30 degree Celsius. At that time, the oil viscosity is high, also means the oil is not that easy to flow back to the compressor. With only one, which is this major oil return passes, the amount would be not enough. At that time, we always create another, which is this assistant oil return valve to ensure enough oil can flow back to the compressor for lubrication. And just for your information, if the outer ambient is low, the compressor is always in high frequency. At that time, always require more oil for lubrication. Subcooling technology. For this one, which is only in cooling mode, the system will control the subcooler from the outdoor unit to indoor unit. And here is the outdoor unit in this frame, and it just connect with two indoor units. So in cooling mode, here the outdoor heat exchanger, uh, the outlet of it already become liquid, which is the first stage subcooling, and then we send this one to get through this subcooler. Actually, it is a preheat exchanger, and then we send this liquid to the indoor unit. So you can find that a partial refrigerant from the main row will get through this EXV and get metering, and then itself will can become cooled down, and then it can absorb heat from the main roll. Then this one will become vapor and flow back to the compressor, and the main roll will become cooled down, and then it can flow to the further indoor unit but still maintain liquid. And here is the question that what is the benefit we can get to make it to be cooler? I'll give you 5 seconds to consider this one. 5, 4, 3, 2, 1.
The reason is that during cooling mode, we need to send the refrigerant from outdoor unit, which is this liquid refrigerant, to the indoor unit to be specified to the indoor unit EXV for the metering. And during the metering process, we also need to guarantee this liquid refrigerant it should be 100% liquid. The reason it is that if it just contain a little bit gas or the vapor, this is also the refrigerant, then it will make the metering process to be a little bit turbulent. And a little bit turbulent also means it will be noisy. And if it just it is 100% liquid, the process is very peaceful. And actually, this noise or the sound can be covered by the fan speed, especially when you set the fan speed to be medium or high. However, when you go to sleep, and always the customer will like to adjust it to be low or even silent. At that period, this fan noise cannot cover the process noise. Then the customer always complain about this. So the benefit for this one is first we can lower the metering noise. On the other hand, if it just contain a little bit gas, also it will cost more power to deliver the refrigerant from outdoor to the indoor. And the power, this one is from the compressor. In other words, if we can maintain or make it to be more cooler, it can also less or lower the compressor power. For our latest TMV system, we can achieve the delta T, which is away from it become gas or vapor. This one we claim it to be 35 degrees Celsius. Bigger size for the heating EXV. First of all, this heating EXV locates at the outdoor unit for the heating metering. Specified locates at the outlet of the outdoor heat exchanger. And also you can find that for our last generation. Here is the EXV. It just bypass with a check valve. Do you know why we need to set a check valve here to bypass this EXV for our last generation? The reason it is that it is in cooling mode, especially when the outdoor compressor is in higher frequency. At that area, the refrigerant flow rate is extremely high. Even this is fully open. However, it is not enough. In other words, the refrigerant still metering at this location, and that is what we don't need. So we need to create a check valve here to let the more refrigerant bypass here or to pass through this area as soon as possible. But for the TMV6, we apply the bigger size EXV and with the fully open. So I just compare on this graph, you can find that it is 40% higher in the flow rate. And also that is the reason why we can cancel this check valve to guarantee more refrigerant can flow through this EXV as soon as possible in cooling.
Enhanced vapor injection for side discharge. First of all, let's focus on this diagram. You can find that here is a subcooler. It is actually a preheat exchanger. This one is from indoor unit, and here to the compressor, and also here is a subcooler EXV, and this is to the outdoor heat exchanger. Then the refrigerant from the indoor unit, actually it already become the liquid, and then this liquid will flow through to the outdoor unit heat exchanger. However, a partial refrigerant just get into this subcooler EXV and get metering. Then we will make this part to inject to the compressor by getting through this subcooler. The purpose of it is just to ensure this part, this injection amount is completely vapor. As for the compressor, it is from Gree, it is rotary, and this is the regular one without the EVI, which is there's one in. After get inside, it will get compressed and then get out. After we turn on the EVI and another in will join here, then we can make the refrigerant to be compressed out. For this one, you can find that we can get a higher refrigerant flow rate. On the other hand, that means we can get a higher capacity, especially in low temperature. And from this diagram, you can also find that there are two EXV for the EVI. Two EXV come together, we can have two 1,400 steps. And just instead of the solenoid valve to control the injection amount, we applied EXV. The reason it is that for the EXV we can avoid the impact just due to the suddenly on off of the solenoid valve to the system, which can ensure the reliability. Similar to the EVI of torque discharge, this time the diagram almost the same, but the compressor, it is from Hitachi, it is scrolled, and here is the EVI off. And when we turn on the EVI, we get another in from here, then we can have a higher refrigerant flow rate to increase the capacity in low temperature heating. And also we apply EXV instead of the solenoid valve, and also there are two EXV even for single compressor. The difference is there are two compressor model. For this one, each compressor also equipped with additional EXV to adjust the amount for injection. This is to avoid the biased refrigerant flow. Variable preheating power for compressor. For this topic, the purpose is to heat up the compressor before commission, which is to heat up the button oil located here. The purpose it is that as the refrigerant, which is the liquid, and the oil, they are mutual solutable, which means they just mix together and we cannot separate them. In order to rotate the compressor, we need to avoid the liquid inside. But for this situation, it is impossible. So we need to make the oil to be heated and make the liquid refrigerant become vapor or gas to flow out. For Jeremy 5, we just apply this oil heating valve, and of course, the power is not that high. It costs about 8 hours to ensure there is completely no problem. And for Jeremy 6, we apply this coil, which is just to rotate the compressor when it is running. But for this preheating, we just input the power or the current into it, just make it to be heat up, and then it will generate a heat, which also to heat up the oil. And with these two together, we can shorten the time by 75%, which is only cost about 2 hours. Then we can finish this preheating. Anti-freeze design of the chassis. At the bottom of outdoor heat exchanger, it is another cycle, which is different from the upper side. First of all, as we know that this area, if it is far away from the top fan, the ventilation also will become small, which means the heat exchange rate also become very low. On the other hand, during defrost, the water or which is from the ice will accumulate it at the bottom, and then it can easily to become ice in the next heating cycle. So we just sacrifice this one and make it to be separate from above. And also you can just from here we can get the hot gas bypass from here, and then we can prevent the ice accumulated at the bottom. On the other hand, as this one just connect the compressor discharge and suction side, it can acting as a gas bypass. Heat exchanger design. First is the partition setting. For Jeremy 6, compared with Jeremy 5, we make the outdoor heat exchanger divided into two partitions, up and down. First, let's focus on the Jeremy 5, which is here. We apply this distributor to distribute the refrigerant into different passes. However, as this is a little bit too long, this is actually the capillary, and if it's too long for mass production, we cannot ensure the refrigerant can divide evenly into different passes, just due to not that easy to control. As for the Jeremy 6, even we apply this distributor, but just due to this lens is only half of that, so the control will become much more easier. And the next is this auto heat exchanger. We apply 3 rows with 7 copper pi. For this one, we can extremely higher the heat transfer efficiency.
Heat exchanger fin design. First, we go to the fin structure. Actually, in the factory design system, there are 3 kinds of the fin, which is the flat, corrugated, means the surface is not flat but just up and down. The purpose of this one is to increase the air turbulence. And the next is the slip, which is on the surface. We just cut lots of the slip. The purpose also to increase the turbulence when the air flow by. And as you know that the higher turbulence, also we can get a higher heat transfer efficiency, right? So from the side view and top view for these 3 structure, a little bit different, just for your reference. And I just confirm from the heat transfer efficiency. So definitely this slip fin can get the highest value, right? Because we can make the air volume to be the most turbulence. And the next is the water stiffness. What is this one? Actually, it's very important when we're doing the heating. So the question, why is important we do in heating? This one is important. Okay, and the reason is in heating mode, always the outdoor will generate the condensing water, right? Which means especially when the outdoor ambient is lower than the freezing point, it will generate the frost or the ice, and then we need to do the defrost, which is to make the ice to become water. And if this water can easily to stick on this fin, it will not be good for the next heating cycle because it will just become the ice quickly again. So for the water thickness, the lowest one is the slip fin because the water can stick on this slip, and the best is of course this flat fin, but just consider the heat transfer efficiency. We will choose this corrugated fin as the UNIX outdoor condenser fin. Next, we go to the corrosion level. Do you know what is this one? It is actually the outdoor heat exchanger, and you can find it. This is the copper tube, and between them it is the corroded fin. I can say that it is completely corroded. When you touch the fin, it will become the debris very easy. So I don't think you would like to become this one, right? The reason it is that if the corrosion level is low, you become this will damage the heat transfer efficiency, definitely, right? And in the design system, we have these 3, which is the you can find the thickness. If it is higher, also we can have a higher corrosion level. The inside structure is almost the same. And for the UNIX, we just choose the golden fin, which already passed 1,500 hours of the natural salt spread test.
As for the inside PCB, and you can find it, here is the GMV5 main board, and here is the GMV6, and it's 37% smaller. As for the fan drive, this time is up to 46% smaller, and also this one is the same even for single or double fans.
That's all for this sharing. If you still have any other question, suggestion, you can feel free to send me to my email address. Meanwhile, you can also scan this QR code to access the sharing presentation. Hasta la próxima. それではまた今度。